So this chapter now focuses on energy transport in the climate system and its parameterization. We talked about the energy deficit at high latitudes, energy surplus in the low latitudes, and the energy transport needed to make sure that the poles don't keep getting colder and the low latitudes don't keep getting warmer. And in the models, obviously, these are explicitly computed if they're full models, because the models compute velocities, winds, ocean currents, temperatures, temperature gradients, various processes on land, ocean, atmosphere, polar, and so on. So they compute energy transport needed to produce the climate that they produce, and hence they are not necessarily parameterizing energy transport itself, but of course, as we mentioned before, they are parameterizing other processes like clouds and rain. Nonetheless, coming back to energy transport, we are here looking at radiation balance as a function of latitude, which is what demands energy transport. Shown are the annual mean as well as the two seasonal mean, DJF and JJA. So you can see the annual mean is almost symmetric, more energy in. So this is the net radiation at the top of the atmosphere. So it is short wave coming in and long wave going out. And obviously, here is the deficit in the thick black line. Negative means net deficit and positive means net surplus. So you have surplus energy in some places and deficit in some places. So we move energy, which is obviously seasonal because sun moves north and south. Polar seasons get cold and warm, and we get changing temperature gradients as well as changing incoming shortwave radiation, equator to pole temperature gradients. So we are looking at DJF when we have winter in the northern hemisphere, so you have more energy transport happening towards the south here for DJF, and negative energy transport in this this is just not transport, this is just radiation balance. I'm sorry. So the radiation balance is negative beyond certain latitude in the northern hemisphere and positive towards the southern hemisphere, but the poles remain negative, as we said. So the polar circle makes a difference, which is also true for the northern hemisphere summer or southern hemisphere winter. So southern hemisphere has a deficit and northern hemisphere has the peak net radiation and deficit at the poles. So the deficit at the poles is a permanent feature, right? Which is what drives the transports. So northward energy transport required can then be directly estimated by determining how much energy has to be moved here to remove this deficit, how much energy has to be moved here to remove this deficit. That gives us total transport required from the low latitudes towards the poles. Positive sign because meridional direction is positive here, moving south against the negative in the negative y direction. Y is typically latitude, then that is negative, but basically it's divergence of energy from the low latitudes towards the poles. And we have components in it. So we have the atmosphere moving as dry static atmosphere. So we haven't done these, but dry and moist static energies can be computed, and we will do that later on. And there is latent energy being moved, where evaporation, there is a net evaporation in some places, and then transport of that energy that is picked up from the surface being condensed in the atmosphere and moved northward. So obviously we have the ITCZ and other mid-latitude storm track features showing up as well, where net energy is released. So a lot of work is done by the ocean and the atmosphere, but you can see that ocean does most of the energy here in low latitudes, and then atmosphere does a lot of the work. Atmosphere does a lot of the work here, and ocean drops off beyond a certain latitude, and atmosphere does a lot of the work. Dry and moist or latent energy. Okay, so specific energy or energy per unit mass can be written as internal energy CVT plus Gz is the potential energy when you hold an air parcel or a water parcel at a height or a depth where it's not neutrally buoyant in a non-rotating framework. Gives us the potential energy, and there are ways in which this potential energy can be released into kinetic energy, which we will get into later. Latent energy is of course related to condensation of humidity plus 1/2 u squared plus v squared, which is the kinetic energy. It turns out that the kinetic energy is typically not a big term at all, as you see here in this table. Amount and distribution of energy per unit surface area in the global atmosphere. This is an estimate that's pretty old, but numbers are quite valid even now. They keep changing because of course global warming and changing equator to pole temperature gradient, especially because of polar amplification, where the warming rates are much more rapid in the polar latitude, especially the northern hemisphere. So internal energy estimated to be 1800 million joules per meter squared. That's almost 70% of the total energy. Potential energy is 700, so less than half of that, 27.3%. Latent energy is much smaller, so there is water vapor in the atmosphere, which is very important for driving the circulation, especially in the tropics with the enormous amount of energy released from condensation heating. It sets off waves and gradients and winds and so on, but still you can see that in the total zonal mean meridional energy, in the global mean energy, that's not that large, so 2.5%, and kinetic energy is basically negligible. So even though everything is moving all the time, winds are blowing, oceans are moving, kinetic energy in the system is not that large. Okay, so that's the 100% adding up to 2565 times 10 to the 6 joules per meter squared. So if we want to look at zonal mean meridional transport, which is what we have typically been doing, we can write it as vector u times density of the fluid, atmosphere or ocean, and mass specific energy. We will introduce now some concepts of eddies, stationary eddies and transient eddies and so on. Should I stop this podcast here? How long am I? 8 minutes. So let me stop this here and then do the eddies and the splitting in the next section. We already got introduced to that a little bit, so let's do that in a little bit more detail. Basically, because winds are not always moving in one direction, they oscillate. Ocean currents do the same, temperatures do the same, humidity does the same. We have to compute net transport across latitudes. So we have to make sure that if there are winds, temperatures oscillating back and forth, then what is doing the net northward transport? So it turns out that there are ways and processes by which the atmosphere and ocean do net transport across latitudes, because this constraint that energy must move from energy surplus regions in the low latitudes to energy deficit regions in the high latitudes is a must. It's a very strong constraint. So even if winds fluctuate back and forth and temperature and humidity do the same, energy and heat must keep moving northward. This is what places many constraints on the patterns we saw in humidity from space and so on, which have these tilting southwest northeast kind of patterns, which are all related to these constraints on how fluctuations, no matter how strong they are or how frequent they must move net energy northward across latitudes. Okay, so we'll come back and look at that.